All right, welcome to our fifth lecture in this course on algebraic topology. We're here at the University of New South Wales, and I'm Norman Wahlberger. Today we're going to talk about two-dimensional objects, continuing on with this thread, and concentrating on the torus and this notion of genus that was in fact introduced by Riemann in the 19th century. So we've been talking about the plane and the sphere so far, so it's time to introduce a few more complicated two-dimensional objects. And the first one is actually pretty simple. It's just a cylinder. And a cylinder is, of course, pretty simple to describe. It looks like this. And it has a round cross-section. And then there's a question of whether it should go infinitely up or not. And we'll agree that it does go indefinitely up and down. So it's a cylinder which is topologically a line across a circle. There's the line direction, and there's the circle direction, and this is our cylinder. We won't give it a separate name. Now sometimes we're also going to be interested in a variant of that where we actually chop it off. So we might also look at a closed bounded cylinder, which is just one that actually has only a finite extent in this vertical direction. And so we could call that I cross S1, where I is the standard interval. I is 0, 1, the closed interval. I probably should mention that there's quite a difference between including the boundary points and not. So when we include the boundary points, we get the closed interval. When we don't include the boundary points, we get an open interval, or perhaps a half open, half closed interval. So the open interval denoted usually by 0, 1, and on the line we would indicate that by putting a round circle, usually sort of an interval with some round circles instead of closed circles. That's the open interval, so it's described by the inequality 0 is less than x less than 1. This is homeomorphic to a line. It may not look like it, but topologically, an open interval is just the same as a line. And we can see that in a number of ways, but a very nice way of seeing it is to look at the function 1 over x. So there's y equals 1 over x. And when x is 1, y is also 1. So it goes to the point 1, 1. And if we then look at what happens to the closed, or rather the open interval, between 0 and 1, that interval there, that's our open interval 0, 1. Then under this transformation, it's mapped to this open half line. So it's mapped, well, 1 doesn't quite get included, but everything above it does. And so we've mapped the open interval to this open half line. Now if we wanted to get a map from the open interval to a whole line, we could just put two of those together. So we could do something like this. We could say, all right, suppose we want let's go from 0 to 2 perhaps. All right, we could take the this branch of the hyperbola that we've just been talking about, and then we could take that same branch and sort of reflect it and put another copy starting here, going down in that direction. Right, and if we did that, well, we would get maybe, it looks a little bit funny, but it would actually be nice and continuous. And then we would get a map, or a homomorphism between the open interval 0, 2 now, to the entire affine line. I know you also all know that you can also do this with a tan function and something like that, but I like to think about it this way because this is purely rational. And you can compute this. You can say exactly what everything goes to and what the inverse is. All right, so that just shows us that when we're talking about this infinite cylinder, we could also think about this as being simply an open cylinder, homeomorphic the same. So when I open, I'm thinking we're not including the top and the bottom here. Okay, the cylinder has another manifestation in terms of some group theory, some baby group theory, and that's going to be an important idea for us, so let's have a look at how this goes. So we think again in terms of the affine plane with our usual coordinates x and y, and we consider our basic translation map. Translation, say to the right, by a 1. So let's call that tau. All right? We've seen that map before. So tau is translation by 1 to the right. And we can compose that with itself, so we get the group generated by tau, which we can sometimes write like this. That consists of all things, maybe write like this. It consists of things of the form tau to the n, where n is an arbitrary integer. So tau squared, for example, will be translation by 2. Tau to the minus 3 will be translation to the left by 3. It's just an example of a very simple group. This is a group of transformations, in this case, of our affine space A2. The identity element is this map that doesn't do anything. That's T0. That's the identity. And the inverse of an element Tn is T to the minus n. Those are the two basic things that we need in any group. All right, so now that we have this group acting on the plane, one thing that we can do is we can think about its orbits. Think about its orbits. So if we're given any point, say x, right there, then the orbit of x is anything that you can get to from x by applying anything in the group. Okay. So the orbit of x, maybe we might call O sub x. It's the orbit of x. And it consists of things of the form tau to the n acting on x, where n is an arbitrary integer. And what does it look like in this case? Well, it just means you can allow to translate it by 1 over here, and then by another 1, and keep going. So, and you can also translate it to the left. So that's what the orbit of x looks like. And now in this picture, the cylinder is visible as the collection of all orbits. So I might say here, the cylinder can be viewed as the space of all orbits. And we can see that by thinking, well, how could we list or label or parameterize all the orbits? Well, what we could do is we could look at a strip a strip between x equals 0 and x equals 1, then every orbit, no matter where it is, will meet this vertical strip. Most of the time, just in one point. For example, this orbit meets it in just one point there. But you could imagine another orbit that meets it in 2 points. For example, here and here. Those be also in the same orbit. And so to get rid of that redundancy, what we could do is we could take this strip and we could identify the left edge with the right edge. We simply glue this point on the one side of the strip to the opposite point on the opposite side of the strip. We identify those points, and then we get a nice representative family for all the orbits. And that gluing operation, topologically, gives us a cylinder. Because that's how we can get a cylinder. We can take a strip of paper, and we glue one edge to another edge. So the space of orbits is a cylinder because we're just gluing the two sides of the strip. All right, so that idea is going to resurface now when we go to something a little bit more elaborate. The main topic of today's lecture, which is the torus. The torus, or a donut, and I'll spell it right this time. Okay, what's a torus? It's a two-dimensional surface. It looks like that. And it's got a round cross section. And topologically, it's S1 cross S1. One way of getting at this using coordinates would be to situate an X, Y, Z reference frame, right, with the origin right in the middle there. X perhaps, Y, Z. And in that case, then, if we looked at the intersection of the torus with the YZ plane, that is the plane of the board, you would get a circle here. In fact, there'd be another circle on this side as well. So that's one natural parameter. There's a natural parameter along this circle. And then the whole torus can be thought of as sweeping or rotating this circle around the z-axis. So it's obtained by, here's the circle C, rotate C about the z-axis. And so then there's two circular parameters involved. There's one parameter around this circle, and there's a second parameter around this circle. And that's why the torus is S1 cross S1. And we'll call it T for short. It deserves a separate symbol. Now, topologically, we don't have to insist on this very regular torus sitting inside Euclidean space. We're allowed to deform it. So we can take our torus and we can deform it. And we can deform it in lots of different ways. We can deform it so that the whole is off to one side. And the rest of it is a kind of like a potato shape. We can deform it so that it's, in fact, the potato shape is more like a tomato. And then this handle piece actually does look like a handle. Maybe I should make it more like a real handle. So in this way, it's starting to look like a sphere with a handle. And that's a very nice way of thinking about it that we'll generalize later. All right, so to give you some practice in thinking about deforming things, here is our problem. Today, problem number 8, I believe. Correct me if I'm wrong. Problem 8 is show how to continuously deform well, I'm going to do something a little bit more complicated than a regular torus. I'm going to have a torus with 2 holes in it. And I'm going to start with this is a 2-hole torus. And this 2-hole torus is hanging on a clothesline. It means that there's a clothesline like this, and it comes through here. Okay, so that torus is hanging, that 2-hole torus, this is a 2-hole torus. Is hanging from a clothesline from one hole. So we want to deform that to this situation where you have the torus is now, or the 2-hole torus is at an angle. Here's the clothesline. It goes through here and it comes out here. And then it goes in that hole and out. Now it's caught in both holes.
How long is that clothesline?
The clothesline is infinite. You're not allowed to slip it off. Oh, sorry. So that's a very long clothesline. You're not allowed to slip it off. That would be a little bit too easy. Oops. Half the battle, at least, is drawing the pictures, I think.
You do proof by picture here, right?
Sorry?
Proof by pictures. Yeah.
Proof by pictures, yes, proof by pictures. All right, so let's just mention these, this generalization of a torus called the n-hole torus. There was an example of it right there. So we've already seen the 2-hole torus, but we can also think of a 3-hole torus. There's a 3-hole torus. And it's just the surface that we're talking about here, right? We think of this object as being made out of plastic. It's empty inside, and it's deformable. And you could either think of it like this, or it's perhaps more usual just to think of it like this. Hope you'll agree that those are the same things. And obviously, we can increase the number of holes arbitrarily. We can make an n-hole torus. Now, these seem like pretty exotic things, but it turns out they come up in practice. And Riemann, in the the early stages of the subject, Riemann realized that some of the surfaces that he was associating and studying in complex function theory were of this kind. And he recognized that the number of holes was an important property. Okay. And he gave this a name, and it's now called the genus. So the genus in this context is, well, it can be described in terms of numbers of holes, but that's a little bit informal. Number of holes, like we've been doing. I'll put quotes around there. But a slightly more careful definition is the genus is the maximum number of disjoint loops on a surface that you can draw so that things are still not disconnected. Maximum number of disjoint loops on a surface which do not disconnect it. So for example, the case of the sphere, there's our sphere, S2. If we draw any closed loop on it, start there, and on the surface of the sphere you draw a closed loop, come back to where you started. And if you take a knife and you cut along that loop, then the thing falls into two pieces. There's an inside and an outside of that loop. So there'll be that piece there and then the rest. So a loop, any loop disconnects S2. That's actually not such an easy theorem to say precisely and to prove. That's essentially a famous theorem called the Jordan curve theorem. And even to say precisely what that is a non-trivial exercise.
I thought it applied to the plane too.
And it applies to the plane too, yes. It's pretty well the same thing for the plane and the sphere. What about for a torus? Oh, but by the way, so what is the genus of the sphere? So G is usually the word for genus, or the symbol. So genus of the sphere, you can't draw any loops. So the maximum number is 0. Okay. How about just now for our torus? Well, now you have to be a little bit careful. If you draw the loop like this, then it will separate it into two. So what we don't want to do that, because we want to try to keep it connected, so we're not going to do that. But what you can do is you can draw the loop in this way. You can start here, then you go around the other side, and back up here, around the ring part of it. And then if you cut the torus along that loop, well, it separates then into a cylinder, but it's still connected. But if you take that cylinder then and you cut an additional loop, then it will fall into two pieces. So in this case, the maximum number of loops is G of the torus is 1. And it's then a similar kind of story if you have a two-hole torus. Then you can cut the two loops in out like this. You wouldn't want to do a loop like this. because that would separate it. Well, you wouldn't want to do a loop on the surface either. Now that piece would fall out. But you can make one loop just like we did for the torus around that ring or around that hole, and then you can do another loop somewhere over on this side on that, and then you have two cuts. And if you cut the two-hole torus up, it will still be connected.
Do we call it in-hole torus T to the power n?
No, I don't think there's a... no, we prefer powers to represent actual products in the sense of topology. So I'll usually say 3-hole torus or 2-hole torus and not have a separate name for it. So here, the genus of this thing, let's call it M. G of M would be 2. So let's talk about some ways in which the torus manifests itself. So a torus as a configuration space.
Is there a reason Riemann didn't define genus as saying homeomorphic to an n-hole torus?
I don't think he had the idea of an n-hole torus in this sense of pictures. I mean, he would have recognized this, but I don't think he thought it that way. He thought rather about the Riemann sphere and these various layers defined by these functions.
I guess he's thinking apart in the complex plane, which can
Yeah, these are, for him, these are all things, these are sort of images of the complex plane, are very closely related to the complex plane, covering the complex plane in some complicated way sometimes. To think of them as abstract objects independent of anything else, I think that came later, probably maybe with Klein. So the torus as a configuration space, I'll just mention this. Suppose you're a robotics engineer and you want to create a simple robot in the plane, okay? And you've got some fixed point there, and you have some arm, with your first arm of your robot, let's call it arm R1. And then you have some hinge here, and then you have another arm, say R2, and then here is the free point. So this is fixed here. That's like your origin, and this arm is free to swing around this pivot point, and this arm here is also allowed to swing freely around this point. And now clearly if you had some mechanism to control these two motions, you could make this point here go anywhere in, well, in this case probably an annular region, right? That's probably about as closest to the origin as you could get with the sizes, and then you could probably get out to about here. So your robot could explore this annular region if you gave it the appropriate instructions. And the appropriate instructions would simply really amount to a number telling us how far to turn around here. So we need one turning number. And then we need another turning number with respect to some reference point here. And these turning numbers are essentially in a circle. And so as far as all the possible configurations of this robot are concerned, the configuration, or the space of possibilities, is on S1 cross an S1, which we recognize as our torus.
Are you allowing three-dimensional sort of?
No, this is just a planar picture here.
Okay.
This is just meant to be a planar, all happening in a planar picture. If it was in 3 dimensions, then it would be more complicated. It's just in a plane. That's quite a different picture from the kind of thing that we had over there.
So what do you do about the fact that two different combinations of those possibilities could end in the same place?
Oh, absolutely. So what we really have, if we're talking about, here's the abstract torus, which is represented by all the possibilities. And the question is, how does that relate to this annulus? Right? So clearly, given any point in this configuration space corresponds to a configuration of these arms, and we'll give a final point. But this map from a point here to a point here is not one-to-one. There will be different configurations over here that map to the same point over here. And a robotics engineer would be interested in that relationship. Because he might want to get at this point in an optimal way in terms of his arms. So there's a kind of an interesting map or function associated to this kind of robotics situation.
So does that give us like an orbit of a group in the same way as the cylinder identification?
Yeah, you could probably phrase it in terms of some group structure. I'm not sure if that'd be the most natural thing, but that might work.
Is the second arm shorter than the first?
In this particular example, it is. But clearly, you could make your robot however you wanted to. Okay, so now our other manifestation, which is going to be rather important, is torus as an orbit space. So what we're going to do here is mimic what we did for a cylinder, and it's very much the same kind of idea. We start with our plane. And then we have our standard translation, the one that we called tau before. Let's keep it. So tau is still translation by 1 to the right. And let's call it maybe tau 1, because I want to also introduce another translation, 1 up, a translation of 1 going up. Let's call that tau 2. So that's by 1 up. And now we can consider both of these translations together, and we can consider the group generated by all these translations. Okay? And it's perhaps easiest to visualize if we think about what it does to a point x. So we're allowed to translate by 1 to the right, so we get that same kind of orbit that we did for the cylinder. Okay, I'll connect them like this, sort of, and also to the left. But now we're allowed to take any one of those points and also translate by 1 up. So we also go up here. And we also go down. And we can keep going in all directions. Okay, so it's what we're getting is a kind of a square grid superimposed on our original grid. So this is the orbit of x. Orbit of x. Under the group generated by both tau 1 and tau 2. And let me say a little bit what that means. So if we have, say, tau 1 to the n and tau 2 to the m of x, what we're talking about here is, you can think of this as being what you get by first applying tau 2 m times to x, and then applying tau 1 n times. But these two transformations commute. It doesn't matter what order you do it. So this is really the same as what you'd get if you started with x, applied tau 1 n times to it, and then applied tau 2 m times. That's because tau 1 times tau 2 equals tau 2 times tau 1. These two commute. So the group generated by them, this group tau 1, tau 2, I guess this is the group generated by tau 1 and tau 2. We can think of this as being things of the form tau 1 to the n times tau 2 to the m, where n and m range through z. So in terms of group theory, we could say that if we call this group, say, G for group, then we would say that G is isomorphic as a group to Z cross Z. All right, so now what we did for the cylinder is we said, all right, we have this orbit. We have this group of transformations. Now let's consider the space of all orbits, right? That was the ultimate thing that we're really interested in. Okay, so what's the space of all orbits over here? Well, every orbit has a representative in this. I'll choose this unit square rather arbitrarily. I could choose any square. If I choose this particular square, then every orbit intersects or meets that particular square. Right. Most of them meet it in just one point. There's a few orbits that meet it in 2 points. For example, if I chose the point y there, then this would also be in its orbit. So these 2 points would both be in the square and in the orbit. And there's another point, even more special. If I happen to choose Z, say, to be on the corner, then the orbit of Z would include not only that corner, but also the other 3 corners. So every orbit, we can say every orbit meets this square in either 1, 2, or 4 points. So let's have a look at that square, and the identification of that square with the space of orbits gives that square an interesting additional structure. So that square that we've been talking about there, I'll reproduce it here. There it is in blue. Okay. So this is now the space of all orbits. But we have to be a little bit careful, because to make that the space of all orbits, we need to make an identification. So the space of all orbits, provided we identify a point on one edge, say like this point, y, with y prime, well, which is in this case just tau 1 of y. Or point W down here. With W prime, which is tau 2 of W, which would be up here. W prime. So we want to identify these 2 points. It means we basically want to glue them together. And we want to identify these 2 points. We want to glue them together. And that includes the special case of the corner, because then the corner has to be identified with that because of that first rule, and also has to be identified with that by the second rule. So the corner will be identified with all the other corners. And what this amounts to, we can think of this in terms of a gluing operation. So we can just take that square and we can say we're going to glue that edge with that edge. And these arrows indicate the way in which we're going to glue them. That means we're going to glue this point at the bottom here with this point at the bottom down there, and this point at the top with that point on the top. And we similarly have to glue these 2 pieces together, and we'll do it like that. And that's the same kind of rule, so that this point here is glued to that point, and this point there is glued to that point. And now that all makes a lot of sense topologically, because now in 3-dimensional space we can just take that square and we can glue the first 2 pieces together to form a cylinder. All right. So I'm taking that edge A and that edge A, and I'm gluing that together. That's now the edge A right there. I've glued it together, and now these edges B and B are still here. They're still waiting to be glued. But edge A has already been glued. So now to glue the edges B, well, we have to take this cylinder and we have to kind of move it around. Like that. So that we can glue B to itself, and maybe there's B there and B there. That's still the edges, the free edges B that still have to be glued. And when we do glue them, then we get a torus. So this is a very important way of sort of unraveling the round torus into a square with opposite sides identified in a precise way. An idea that I think probably goes back to Klein. So there's some underlying geometry here. So an underlying geometry is the idea of the tessellation of a plane. A regular tessellation, let's say. So by tessellation we mean where we separate the plane into lots of copies of the same thing. And a regular tessellation means that the same thing, the fundamental object, is a regular polygon. And I suppose you all know that there are not a lot of regular tessellations. There's a tessellation by squares. There's a tessellation by triangles. Okay. By equilateral triangles. And if we want a regular polygon, then there's only one more, which is closely connected with this one, which is in terms of hexagons, regular hexagons. I could probably draw, there's a hexagon there, so you'd use this picture to draw this one, but honeycomb kind of pattern. Hexagons. So those are three. That's it. Those are the three regular tessellations of the plane, and we've used basically this one. We've taken this one and essentially used the group of symmetries of this to create the torus. This one here, it's a little bit more problematic to make a gluing. If we tried to take a piece like this and glue opposite sides, we'd be perplexed by the fact there's only three sides. So if we wanted to glue them, there'd be one left over. It doesn't seem to work too well. But the hexagon is quite nice because it has an even number of sides. And we could say, well, we could do exactly what we did for the square over here in this case. So what does that mean? Well, we consider translations, the translational symmetry group of this picture here, which has this kind of, that would be one translation that preserves it. And then there's another translation in this direction. And there's another translation in this direction. Those three translations are not independent. You can kind of see that if you do this one and then this one, it's the same as doing this one. Okay, but anyway, it's a nice symmetry. So one thing that we could do is we could look at this. So problem 9, show that by gluing, okay, here's our hexagon. I'm just going to take one of these copies. Yeah. Gluing this hexagon in the following way, we could glue that side to that side. And say that side to its opposite side. And this side to this side. Show that by gluing this, you get a torus. You can actually make a model if you like. Okay, so at the end of the 19th century, people started to realize that surfaces, at least closed and compact surfaces in three-dimensional space, so the compact surfaces could be listed. The compact surfaces that you could actually make a model for in three-dimensional space. And there was the sphere, obviously. There was the torus. There was the two-hole torus. And so on, three-hole torus, and so on. And that was it. So if we want surfaces which are compact, compact means, I'll say a little bit more about this next time, but it means closed and bound. It means that, first of all, it fits inside a big sphere. It doesn't go off to infinity. And secondly, it means it doesn't have any open pieces, that all the limit points are included in the thing. It's not like an open interval, it's more like a closed interval. And there's no boundary point, so that every point looks like a little two-dimensional part of the plane. So that was a kind of a major theorem, but that's really only half of the story. There's the other half concerns surfaces which cannot be fit into three-dimensional space, and those are the non-orientable surfaces, and we'll talk about those next time. So I'll see you then.